Hi, this is an update to SCAD-DTS, the Simulation Control Animation Training and Design Server. So what I've done is just reconcile the different circuits so that it's easier to get access to it. So if I sign in and let's say if I go to one of the top projects and select the system, and then we get the nodal diagram over there after having selected this particular circuit. Then the engine and the components, so whether the fluid component and the gas component, once you've selected water and air, then it's a single phase engine. If for some reason I wanted to get two-phase system, then I would select water phase, and that would give me the multi-phase engine. And in doing so, then the thermodynamic states and properties are calculated, as opposed to using the constant CP, specific heat, of the fluid in the energy transport calculations. So if I go back to just the water component, for instance, then it's single phase. If, for instance, it was say R410A, then again it's multiple phase, but be using the R410A thermodynamic properties. If I use say hydraulic oil, then it's single phase, and then it uses the specific heat of the fluid. That can easily be adjusted. Like for instance, if it was appropriate to have the thermodynamic tables and the calculations for another fluid, then it can be added to the system without a problem. So if we go back to water, I suppose. So that's the main part of it. I think I'll leave it like that. That's just the update, and if I go through the motions of running this particular system, this circuit. So if you go to the control page and select runtime and start, you go back to the circuit, you can bring this up and you can see what the properties are at the particular nodes and links of the system. So for instance, if I select node 3, then I get the enthalpy, the pressure, temperature, the control volume, and there's a property here which is the heat transferred into the node, and that's used in different simulations. So for instance, in the case of heat exchangers, the heat gets transferred between one system and another, and you'd see the heat transfer in this property here. If I look at in this particular case, if you're not familiar with it, then the green is atmospheric pressure and the blue is pressure source. So for instance, 5, that's the pressure source, and as a result you can change the pressure. In this case, like in the case of node 1, it's 14.7, and that's governed by the atmospheric pressure associated with the circuit, and that's defined in the environment. So we have here 14.7 is the atmospheric pressure. The ambient temperature is 59 degrees Fahrenheit. Default control volume. The component is a fluid, fully fluid, there's no gas. And this is the specific heat that's used in the calculations. The density, and then this is the iteration rate and viscosity and roughness. Okay, so if we go back to the circuit, so we can see, let's say, let's have a look at 4 as well. Okay, so in this case, the let's have a look at the flow rate. Okay, that's the flow rate through the system. Now you'll notice that normally the frictional pressure drop for like between 1 and 2 is relatively small. Let's see, no, 2. Oh, it's reverse. That's linked to. Okay, so yeah. All right, so I think the pump is off. Yeah, the pump is off. And so what we have is the pressure from the pressure source at 70 psi is being circulated through the system. So if we look at link 4, then the valve is open and I've got a flow of 49.371 pounds per second, but it's going back through the pump into the atmospheric pressure. It's also split going this way, so it goes through a downstream pressure control valve. If we have a look at say link 3. Okay, link 3, the flow rate is 18.4 and the valve is fully open. So it's trying to regulate, and it's trying to regulate, let me see, it's downstream pressure regulating, and it's for 28.19. Trying to regulate this to around about between 20 and 30 psi. So if I increase the pressure, let's say to 100 psi. Okay, so the valve goes to 0.94. Now it's regulating, and it's regulating with a gain of 0.2. Otherwise, you can get numerical instability. But this is related to the PID controller aspect of the simulation of the downstream pressure regulating valve. So now we're into the 21 psi range, and so that's the reason why we're regulating to 0.94. The flow rate has increased in the reverse direction to negative 12.771, and this is the normal direction of flow. So if we actually start the pump, and we can do it graphically using this tool here, start the pump, and now we have a positive flow of 23, and the pressure regulating valve is at 0.85, regulating the pressure between 20 and 30 psi. So now you can also go to the plots page. These are the parameters that are can be plotted. So control plot. oh, it's the range. The range is to 1.1 and we're at 50, 70. So that's better. So the plot page, the minimum value and the maximum value can be changed. And so according to whether or not what range you're in, then you need to adjust the maximum minimum values. So like for instance, I can change that to say, I don't know, 20. Okay, and you get more magnification. Now if I go back to the circuit, so if I go to control in here, then let's say I change this to say 130. And if I go to the plots page, then you see the reaction of the pressures and the flow rates within the system. So you can adjust that to increase it to say 90. And then you can do the same thing again. Just go back and change it to 100. And plots. You can see that the variation in pressure throughout the system. So that's one aspect of the updates, and together with the change of determining the phase, the engine of the system. Yeah, I think that'll do for now. Thank you for visiting.